Hey there, welcome back to the channel. So we are back, and this is the next part, which is interlude process API. It's the eighth part, but not eighth part. It's just something on uh, the website, the Wisconsin Madison website. Yeah. So we'll just get started. So we have a lot of time, and the problem is that this is a lot bigger and something that we need to read very carefully. So we need to hurry up a bit, but definitely we are not going to skip anything much since it is a lot of code. We might be able to, you know, just skim through it a bit. But okay, interlude process API. Okay, interludes will cover more practical aspects of the system, including a particular focus on operating system APIs and how to use them. If you don't like practical things, you could skip these interludes, but you should like practical things because, well, they are generally useful in real life. Companies, for example, don't usually hire you for non-practical skills. Cool. Also, another thing, I had three doubts yesterday, and I actually covered all of them, like off camera. So, the first one was about what is a stack pointer and frame pointer that they mentioned. Definitely, I know what a stack pointer is, but just wanted to confirm in the context of operating system. Maybe it might be something different, right? Stack pointer definitely points to the top of the stack. Frame pointer is supposed to be the base of the stack, so as to know where the boundaries are, so you can find the constant variables that you have declared easily, something like that. I get it. It's the base of the stack. That is. The next thing was miscellaneous control. It talked about miscellaneous control. So there are a few different things that we do. Okay, I should just do this. There are a few different things that we do. First is a few different things that an OS needs to do, like the interface that we need to provide. It should be able to create a process, delete a process, um, what was the other thing? Yeah, wait, and then return the status. And then this was miscellaneous control, right? Miscellaneous control was about just stopping a process and then resuming it whenever we want. So that's it. It's nothing deep. Yeah. I was not able to understand it yesterday because it was a lot similar to wait function. So, but a wait is more like a parent waiting for a child process to complete, right? But miscellaneous control, we can just pause any process that is running. So next was where does the parent process create address space for the child? Well, uh, a new address space is created, which is completely similar to the parent process. So we don't have to worry about like the child process becoming bigger than the parent process or something. You know. So that's cool. That's chill. But okay. So I guess all of the doubts are cleared. So we can start again with the new stuff. Something technical, which is fun for me, you know. Okay. Yeah. In this tutorial, we will discuss process creation in Unix systems. Unix presents one of the most intriguing ways to create a new process with a pair of system calls, fork and exec. I have idea of what they are. A third routine, wait. Yeah, wait function as I talked about it. Can be used by a process wishing to wait for a process it has created to complete. We now present these interfaces in more detail with a few simple examples to motivate us, and thus our problem is how to create and control processes. What interfaces should the OS present for process creation and control? How should these interfaces be designed to enable powerful functionality, ease of use, and high performance? Okay, the fork system call. The fork system call is used to create a new process. However, be forewarned, it is certainly the strangest routine you will ever call. Most recently, you have a running program whose code looks like what you see in Figure 5.1. Examine the code, or better type it in and run it yourself. Well, okay, we admit that we don't know that for sure. Who knows what routines you call when no one is looking? Oh, okay, they are talking about like the strangest routine, okay? But fork is a pretty odd no matter how unusual your routine calling patterns are. Okay. So we have some code over here. I'll copy it. Uh, yeah, I can just copy all the numbers and then I'll just remove all the numbers that's not at the beginning. Okay, so I just go. Then I should create this over here. Maybe I can create something like. Oh, by the way, it's not cheat or something. I just thought it's cheat sheet. I was trying to read about the assembly stuff. Yeah, I did it for the project. So let's create a directory itself where we will test some stuff. Right, cool. So this is what should we call it? Fork. Let's call it fork.c. Okay, I'm not going to write it the same thing. Just go over here and I can see that we have a number at the start. So I'll just go boom boom. What's I should learn regex, like how to represent a number. Is it one? Wait, this must be it. 129, right? Something like this. Yeah, cool. And then another 129 and a space. Boom. So this is solved. And then we have still some stuff left, which is 129. Boom, boom, cool. And we still have some stuff left. This is probably like the worst way to do it, but I'm just trying on my own, bro. It's not it's not much, but it's honest work. And then I hope okay, I just do it manually. Okay. Boom, boom. Yeah, so we have int this, move this ahead, boom, if condition, move ahead, else condition, move ahead, this, move ahead. Did I delete something? Wait, no, it's just a new line. Okay, boom, boom, boom. Okay, cool. So this should work. So clang fork.c and add a out. Hello, process ID is 914, parent of 916, parent of 916, PID this child. Okay, so what it does is that to create a fork, fork is to create a copy, right? So create a, yeah. And remember, fork is to create a copy at that specific instance. So copy is created, and if RC is less than 0, that means fork failed, so it will go inside this. And since we don't see anything over here related to error, like related to fork failed, so that means it worked. Yeah. Else if RC is equal to 0, that means it's the child process. So that's when it went inside. So there are two processes that will be running from this point. So it's a child and it's a parent. That's what I think. And if it is a child, it will go inside this. And if it's a parent, it will go inside this. Right. Cool. So hello, this is cool. This is common. So this is the parent itself, PID 940. Parent of 916, PID 940. So parent, okay. Int get PID. Okay. Uh, this is ID. Parent of RC. Okay. So the RC that we get, the value that we get is the process ID of the newly created process. Okay, so this integer is a newly created process ID of newly created integer. So like it's an integer that holds the value of the newly created process, its ID. Okay, cool. Very simple. Okay. Boom, down. Those are pretty big numbers. It's the same thing. Okay, let us understand what happened in more detail in P1.C. When it first started running, the process prints out a hello message. Included in that message is its process identifier, which is known as PID. The process has a PID of 29146. In Unix system, the PID is used to name the process if one wants to do something with the process, such as, for example, stop it from running. So far, so good. Cool. Now the interesting part begins. The process calls the fork system call, which the OS provides as a way to create a new process. The odd part, the process that is created is an almost exact copy of the calling process. That means that to the OS, it now looks like there are two copies of the program, P1 running, and both are to return from the fork system call. The newly created process called the child, in contrast to the creating parent, doesn't start running at main, right? It starts from the the fork itself. Yeah. Like you might expect, note the hello only got printed out once. Yeah, it's the parent printing. Rather, it just comes into life as if it had called fork itself. Right. Cool. We have the new process. So I understand pretty much all of the stuff from it. The odd process that is creating almost exact copy of the. Yeah, maybe I can highlight the odd part. The process that is created is almost exact copy of the. Yeah, I can highlight this. Cool. Cool. So we have another thing. So RC fork, RC error, else if RC child PID, new process, integrate PID, calling fork and wait. Int RC equal to wait, null. Parent of this, let's see, wait this. So wait is going to do, okay. So first, I think what we should run is, will this work? Oh, it worked. Okay. Why didn't it give me about wait itself? Wait, both commands marked no under external do exist externally but are implemented as scripts using a built-in command of the same name. Okay, I don't get it. See the built-in command description in the overview shell man page. Shell built-in commands are commands that can be executed within the running shell, not the interface of CSS. Built-in commands, the command is executed in a subshell if it occurs as a component of a pipeline. Okay, okay. I'm not going to go on this tangent again. Yesterday it was a big tangent, but yeah, today I need to sleep. You might have noticed the child isn't an exact copy, specifically, although it now has its own copy of the address space, that is, its own private memory, its own registers, its own PC, and so forth. Uh, its own PC, program counter, yeah, okay, and so forth. The value it returns to the caller of the fork is different. Specifically, but the parent receives the PID of the newly created child, the child receives a return code of 0. This differentiation is useful because it is simple than to write the code that handles the two different processes two different cases as above. You might have you might also have noticed the output of p1.c is not deterministic. While the child process is created, there are now two active processes in this system that we care about. Okay, so it's not deterministic. With the child process created, there are two active processes in the system, right? Assuming we are running our system with a single CPU, then either the child or the parent might run at the point. Example about the parent did first and this. Okay, 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 cool, cool, cool. The CPU scheduler. Okay, so here we get the hello, we get the child, and then we get the parent. Okay, the CPU scheduler, a topic we'll discuss in great detail, determines which process runs at a given moment in time because the scheduler is complex, we cannot usually make strong assumptions about what it will choose to do, and hence which process will run first. This non-determinism, as it turns out, leads to some interesting problems, particularly in multi-threaded programs. Hence, we'll see a lot more non-determinism when we study concurrency in the second part of the book. The wait system call. So far, we haven't done much, just created a child that prints out a message and exits. Sometimes, as it turns out, it is quite useful for a task, uh, quite useful for a parent to wait for a child process to finish that it has been doing, right? This task is accomplished with the wait system call, or its more complete sibling wait PID. So figure 5.2 for details. Okay, 5.2 is above one. Did you use wait PID, right? No, it's just a wait. Wait, what? Wait, what? Wait. Okay, let me try wait PID. There are two mentions of wait PID. First one is over here. The second one is in there. Okay, sort of was cool. Done. In this example, P2.c, the parent process calls wait to block, that is, delay its execution until the child finishes executing. When the child is done, the parent becomes unblocked in wait and returns to the parent. How does the parent, how does the scheduler know that this particular process is a child process for this? I mean, it must be keeping a track of who called it and whatnot. But still, there must be something, right? It was something that we saw yesterday, right? It had the, what do we say? Let me just open like a CD, dun, dun, my documents, notes, OSTP. Let open up this and wait, where did it go? Yeah, message to parent process. Okay, maybe it stores it over here, like who was your parent process that invoked you, right? So that's possible until the child finishes executing. When the child is done, the parent becomes unblocked and wait returns the parent. Adding a wait calls to the code above and makes the output determine. Wait, what if the parent called multiple processes? Yeah, even if they did, you have to still. Should I try it? I should try it. This is healthy. This is good. So and when fork.c is done, then we'll say this file is more like testing one, testing.c, not py. Do I need something for? Yeah, just do these. Yeah, okay. So So if I want to get the ID for the current process, I have to do this PID, right? Hello, get PID, right? Cool. So if I were to do add wait, int RC wait is going to wait, a wait, right? And I'll just print it. Right, cool. Printf, yeah. Oh, sorry. I just want to print that process, whatever it is. Get PID should work, right? The integer of get PID, cool. Then return 0. This will print the current PID, right? Print A. Not Python. Clang testing1.c and then a.out. So I should state, okay, printf, yeah. My God, bro. Okay, I should add some new lines to it. Or I could have just done this, then percentage d, and then replace it with percentage d slash n. Wait, escape. What? How do you do it? Oh, is it already done? I did it. That is correct thing, right? Wait, what? Yeah, I did not recognize. Cool, cool, cool. I'll just do d slash d slash. I'll escape n. But then this is just escaping this. Yep. Okay, got it. Cool. So what is it waiting for? So we have b is equal to 0, c is equal to 1032. Wait, it's jumbled a bit. Okay, cool. No problemo, no problemo. Oh, it's going to fork. So A is being created, and then the the child process then creates. Okay, okay. This was a really bad test. Okay, I should not go ahead with this. I got it. I understand my problem. But I will note down like what if we wait for a single process? Or is it that like a parent can only have a single child process? No, it can have multiple, right? Then how do we write it? Because if I were to write another fork, then it will just create two new processes, one for the original parent and one for the new child. So how do we create multiple processes simultaneously? Is there a function call that does this? I mean, there must be a way, like something, something modification of fork, but Okay, I'll just write it down. So, how do we create multiple child process simultaneously? I'll also write down the timing where we are messing up, which is 25:00. It's 25 minutes in. Cool. Also, one other thing that I wanted to note down was what was it? It was something important. What was it? 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 Child process. Multiple process simultaneously. Yeah, right, right. If we are able to create one, what if, what happens? What happens if we wait for only one? I mean, if there is, if waiting for multiple processes is feasible, I think it's up to the scheduler or whatever, right? I'm not really sure how we will call multiple processes. There must be a function call that will just fork a bunch of clones, right? That makes sense. Like you can't do it with a single fork system call because fork is used to create a child process from that point, and if you were to write another fork on the next line, two processes will be created, one for the parent and one for the this. And wait can be only for one process. Is that it? Okay, let's just keep reading. So I'll most likely read about this. You might have noticed the child isn't an exact copy, so okay. You might have also noticed the output P1C is not deterministic and the child process is created. This okay, I read about this, okay. So yeah, I've also read about this. Yeah. In this example, P2.C, the parent calls wait to block that is delayed execution until the child finishes executing. When the child is done, the parent becomes unblocked and wait returns in the parent. Adding a wait call to the code above makes the output deterministic. Can you see why? Go ahead, think about it. Waiting for it to think and done. Then it's easy because wait forces you to wait for the child process, and then it will run the parent process like continue. So it's synchronized. Something like memory ordering. What was the one that used to wait for it? Uh, okay, it's right here return. Memory order acquire. Yeah, it will wait for it to acquire every single thing and then it will run. Right. Memory ordering acquire. Yeah, it's a C++ thing. If you're not familiar with it, there are different types of memory orderings for uh, uh, this. What do we say? Oh my God, I'm just forgetting words. Like I know the concept, but I'm just forgetting words. Maybe I should get better at remembering words and all. But okay. What do we call the lock semaphores? There's a one thing that locks. What was it? Mutex. Yeah, it's a type of memory adding that you can add to a mutex. Like you can tell the mutex like how should we do this stuff, right? It's not mutex. It's lock free. Atomics. No. Yep. Yep. It's atomics. Atomics. Oh my God. I'm so embarrassed right now. It's atomics. It's not mutex. It's atomics. Yeah, atomic variables. You can pass what type of memory ordering you want for the atomic operation or whatever. Yeah, there are six different types. One is not really used. I'm just showing off my C++ knowledge of memory ordering. It was a cool thing. C++ concurrency in action is a great book though. Like I learned it from there. Chapter 5, memory ordering, very cool. Crazy book though. I had to focus a lot of time on that because a lot of new concepts. Yeah, Okay, let's get back to the video. No one is really watching this, but okay, if you are watching this, 30 minutes mark. If you are watching this, just don't. No, there isn't going to be anything useful for you here, right? Listen to me, Broski. There is not going to be anything useful for you over here. It would be better if you focus on your own stuff. Uh, go ahead, find a project that you can work on. Uh, maybe talk to your parents. Whatever. Something that is fun, something that is more meaningful instead of watching a stupid YouTube video. Or maybe you just like hearing me out when you're working on something, like a companion or something. Well, that's okay. Hey, Broski, you know. Okay, let's get back to the video. That is a wholesome part. Okay, adding a wait call above this, waiting for you to think, and done. Boom. Okay. So with this code, we now know that the child will always sprint first. Why do we know that? Well, it might simply run first, as before, and thus sprint before the parent. However, if the parent does happen to run first, it will immediately call wait. This system call won't return until the child has run and exited. Thus, even when the parent runs first, it politely waits for the child to finish running and then wait returns. The parent prints its message. Cool. Finally, the exec system call. The final and important piece of the process called creation API is the exec. Sorry, is the exec system call. The system call is useful when you want to run a program that is different from the calling program, right? When you don't want a child process, kind of like you don't want a copy of your current process, right? So there are few cases where wait returns before the child exists. Wait returns before the child exists. Okay, exits. Read the man page for more details. As always, and beware of any absolute unqualified statements this book makes, such as the child will always print first, or Unix is the best thing in the world, even better than ice cream. Okay, it's not better than an ice cream. Come on. Have you even tried the uh, double double chip choco hazelnut, double dip blast or something? Yeah, there's ice cream from Arun ice cream that I get over here. It's I don't know what it's called, but it's something around like it's a biscuit, but it's not really a crunchy biscuit. It's a soft one. It's kind of like a brownie or something. Uh, and then you have ice cream in between, and it's just oh my God, I love it. Okay, let's get back to the video. Okay, let's going to watch this. I'm embarrassed now. Okay, there are a few cases where wait returns before the child exits. Okay, I already read that. On Linux, there are six variants of exec: execl, execlp, sorry, execlp, execle, cv, cvp, sorry, vp, and vpe. So L, LP, LE, V, VP, VPE. Okay, and then we have another code. Okay, let's read through this as quickly as possible. We have half an hour, I think. Yeah. Yeah, okay. RC fork, RC this for fail. If RC is equal to 0, this is child to new process. Child PID, get PID, character my argument. So we get WC. WC is a program. It's another process that is available to us. We can run WC, right? We have WC in Unix also. So if I were to do WC on, let's see, what do I have? WC on fork.c. So I get this. I don't really remember. Is it 417 characters, 54 words, 17 lines? 17 lines, 54 words, 417 characters, 10.txt, and I'll just add A. Okay, so this should give me the output of, let me see, two lines, three words, seven characters. Is it seven characters though? One, two, three, four, 5, which is new line, 6, and 7, which is new line. If I were to add this, so 7, 8, and 9. So this should be 9 now. Yep, cool, got it. Understandable. It's not necessarily new line, it's the end of the line or whatever. New line, yeah, sure, new line. But then why don't I see new line for the last line? Because it's not present. Or is it present? Is it a tab? Is it a null terminator? Oh, it's a null terminator. Okay. Oh wait, oh my god. I'm still on this. Okay. I'm so sorry, boss. You did not miss much. Okay, cool. I just read this paragraph. Okay. Yeah, cool. Oh my god, that might have messed up a bit. That might have been absolutely awful. Okay, so I was reading about this. So else if RC this and character takes some arguments. In the first is uh, it not get the ID character this is a yeah, okay. It's not taking arguments, it's just creating an array which we will pass to this process as arguments. So exec CVP, so my argument is 0, which is WC. WC is another process, right? And then we pass these arguments, which will have my arguments. So this will have the entire thing, which will be the process name again, the parameter, like what file do you want input file, and then null. What is null? Mark end of an array. Okay, it's to mark the end of an array. Okay, cool, cool, chill, chill, cool. And then this shouldn't print out. Okay, this shouldn't print out, so this should end over here. So when you call an exec, it just ends at that place. It creates a new process and then it stops, runs what count. Yeah, okay, this impd.c is only useful if you want to keep running copies with. For example, calling fork impd.c is only useful if you want to keep running copies of the same program. However, often you want to run a different program. Exec does that. In this example, the child process calls exec vp in order to run the program wc, which is the word counting program. In fact, it runs wc on the source file p3.c, thus telling us how many lines, words, and bytes are found in the file p3. And when we run this, hello child, and then 29 lines, 107 characters, sorry, 107 words, and 1000 characters. The fork system call is strange. Its pattern in grand exec is not so normal either. What it does gives the name of an executable. Okay, so it takes the name of an executable, wc dot wc dot wc. Okay, so if I were to try this, so first of all, if I do a dot out, I get this. It's a very big output. Okay, let's write a simple program. Right, hello world. Hello world. See, so yeah, just printf. If I just create, so a dot out is created, and if I do a dot out now, it will print hello world. And if I were to write testing2.c, oh god, I'm messing up include every single time though. What is happening? Wait. I actually have a habit of writing the function name on the next line as compared to on the return type, but I think I need to change that because I thought it was a good design pattern, but it's not. Just wait. Yeah, just take it. Well, who cares? I don't really care. Like loading all these programs is like nothing to me. I have a lot of RAM, I have a lot of compute. And then exec VP. So I'll create this. Okay, yeah. I'll create character array, my arguments. It will be of size 3. And then my arguments 0 should have the process which we are going to run. It will be the executable that will run, right? Hmm. What did it do? They did WC, right? Cool, cool. So we can try just a dot out, but it won't be able to recognize it, right? Let's try. No? Let's try. You never know. My args1 should represent what is the parameter to it? Well, it's nothing. Yep. And my arguments, well, I can just do this, right? Yeah, I can just do that because it doesn't take any arguments. That's like cool, chill. I just give it a 2. And then execute VP and my arguments, the process name, and then arguments to it, which is my args, cool. And I'll just add just in case, so printf, this shouldn't run. Cool. I did not have return 0. Okay, it compiled. And if I, oh my god. Okay, so I need to compile clang hello.c and then output it to hello dot o. Clang hello.c, that's what I meant. Broski. Yeah, and if I were to do hello.o, yup, I have to make changes in testing2.c because it will just do it itself. This shouldn't run. Okay, that thing still ran. What the f? What is exec VP for? Provide an array of pointers to non-terminated strings that represent the argument list variable to the new program. The first argument by convention should point to the file name associated with the file being executed, right? The array of the pointers must be terminated by a null pointer. Cool. I need to understand what the return value. If any of the exec processor returns an error, will have occurred. The return value is not small. The global variable there will be set to indicate the 0. That's one. Okay, okay, cool. So I'll just check for that, right? Cool. Into return value. Or just RC. It failed or some shit. Okay, it failed. Why did it fail? Did you not get the file? Should I export the file as executable or something? Okay, let's try that. So if I have hello.c, I'll just execute export hello. So there is nothing hello, right? Uh, Wait, if I were to export the path, so okay, ls dash la. No, sorry, I wanted to repeat it. Yeah, okay. So export hello is equal users gots downloads testing hello.o, and if I were to end this, and if I were to write hello, will it run? Okay, it's not, because it's not considering that as something to run, right? If I were to do this though, still no such thing. Okay, because it's a variable for them. It's not an executable for them. Right, cool. If I were to do echo hello, then yeah, that is the path. Cool. Hmm. How to export a executable. Yep, that's what I should search. There might be someone, like, if you're watching this, maybe you might know it, and okay, I was just going to go on a tangent, like, comment down if you know the answer to this, you know. But okay, yeah, it's not really unique system. No, let's whatever. Just do it. Just do it. How to export executable? Yes. To export an executable, you typically compile your code using local language C Sharp 6. I already did that. It's okay. Wait, if I were to do chmod plus x, what extra permission does it get? Yeah, it's the same because it's already an executable. Raw. I'll just show what I've been trying or something. Safari, Claude. I'm going to Claude because I don't have a lot of time. Come on, bro. Yeah, okay, I have a life. You too should get a life. And then testing 2.3. Oh, it's such a into the root. Is that it? Because it doesn't know like the current directory or something. So I'll just compile the clone. Let's go. Let's go. So okay, cool. I understand exactly now. Cool. This it's ordering current, this, that. Okay, at Lamson, as Lamson states in his well-regarded hints for computer systems design, get it right. Neither abstraction nor simplicity is a substitute for getting it right. Neither abstraction nor simplicity is a substitute for getting it right. You should always get it right means. Sometimes you just have to do the right thing, and when you do, it is way better than the alternatives. There are lots of ways to design APIs for process creation. However, the combination of fork and exec are simple and immensely powerful. Here, the Unix designer simply got it right, and because Lamson so often got it right, we named the law in his honor. Oh, okay, Lamson's law. Tip, getting it right. Oh, great, Lamson, GG Lamson. W in the chat for Lamson. Okay, so it loads code and stuff. Okay, yeah, the fork system call is strange. It's button curly. Exactly is not normal either. What it does gives the name of exec gives given the name of an executable WC and some arguments p3.c, it loads code and static data from that executable and overrides its current code segment and current static data with it. The heap and stack and other parts of the internal memory space of the program are reinitialized. The OS simply runs the program, passing in any arguments as the argument v of that process. Thus, it does not create a new process, rather, it transforms the currently running process, formerly P3, into a different running program, WC. After the exec in the child, it is almost as if P3.c never ran. A successful call to exec never returns. Okay, so it's just wiped out. Boom. Cool. Of course, one big question you might have: why would we build such an odd interface to what should be simple act of creating a new process? Well, as it turns out, the separation of fork and exec is essential in building it in a unique shell because it lets the shell run code after the call to fork, but before the call to exec. This code can alter the environment of the about to be run program and thus enables a variety of interesting behavior. It lets the shell run code after the call to fork. The shell run code after the call to fork, but before the call to exec. This code can alter the environment of the about to be run program and thus enables a variety of interesting features to be readily built. The shell is just a user program. It shows your prompt and then waits for you to type something into it. So it basically what it does is that it takes an argument, executes like it must be using a fork, right? A new, I mean it shouldn't be using it must be using a fork and a wait, right? That's what makes sense. It creates a copy and then it runs it and it waits for it, and when it's done, we just go into the infinite while loop of asking for new user input. Right? That's what must be happening, right? The shell is just a user program. You then type a command that is the name of the executable program plus any arguments into it. In most cases, the shell then figures out where in the file system the executable resides, called fork, to create a new child process to run the command, call some variant of exec to run the program, and then waits for the command to complete by calling wait. When the child completes, oh right, oh my god, I got it. We run a fork so that then a copy is created, and then we run exec again. Because that fork, the copy, we don't really need the variables inside it, right? We need a completely new thing. So then we run exec, so that stuff is overwritten. Cool, cool. I got it. Okay, I'll highlight this in the simple program. Highlight this. The shell then figures out where in the file system the executable resides. Cool. When the child completes the shell, returns wait and prints out a prompt again, ready for your next command. The separation of fork and exec allows the shell to do a whole bunch of useful things rather easily. Uh, the separation of fork and exec allows the shell to do a whole bunch of useful things rather easily, right? For example, wcp3.c, pipe it into new file.txt. Yeah, this is simple. wcp3.c, we just pipe whatever the output of this is into a new file. And there are lots of shells, TCSH, Bash, ZSH, to name a few. You should pick one, read some man page and learn more about it. Oh, well, I think we have Zish in Mac, right? I am using KSH at my work, and I have Bash in my laptop. Which one should I go for? Bash. Yeah. Bash is the most widely used one. Yeah. But I've heard Zish is great too, so maybe you never know. No. In the example above, the output of the program WC is redirected into the output file, new file.txt. In the example above, the output of the program WC is redirected into the output new file.txt. The greater than sign is how said redirection is indicated. Yep. The way the shell accomplishes this task is quite simple. When the child is created before calling exec, when the child when the child is created before calling the exec, the shell, specifically the code executed in the child process, closes the standard output and opens the file new file.txt. By doing so, any output from the soon to be running program WC is sent to the file instead of the screen. Open file descriptors are kept open across the exec call, thus enabling this behavior. Right, cool, got it. Yeah, there are file descriptors that are basically like, this is a read descriptor, boom, this is a write descriptor, go ahead, use this file descriptor to run the, whatever that thing is. Yeah, okay, cool, cool, cool. The reason this redirection works is due to an assumption about how the operating system manages file descriptors. Specifically, Unix systems start looking for free file descriptors at zero. In this case, stood out file number will be the first available one and thus get assigned when open is called. Subsequent writes by the child process to the standard output file descriptor, for example, by routines such as printf, which I don't understand this part. Okay, wait. I need to understand this part though. So I have how much of it left? Okay, it's not much. I can complete it. So this is one. So this is a summary. That's fine. One, two, three, four. Okay. So I need to understand this in depth. Okay, it's going to be 1 o'clock. Uh, 15 minutes in. Okay. I think we should go ahead and complete it. In the example above, the output of the program WC is redirected into the output file new file.txt. The greater than sign is how said redirection is indicated. The way the shell accomplishes this task is quite simple. When the child is created before calling the exec, the shell, specifically the code executed in the child process, closes the standard output and opens the file new file.txt. By doing so, any output from the soon to be running program WC is sent to the file instead of the screen. Open file descriptors are kept open across the exec call, thus enabling this behavior. Figure 5.4, page 8, 5.4. Yeah, okay. Figure 5.4, page 8 shows a program that does exactly this. The reason this redirection works is due to an assumption about how the operating system manages file descriptors. Specifically, Unix systems start looking for free file descriptors at zero. What do they mean by this? Specifically, Unix system in this case, stood out file number will be the first available one and thus get assigned when open is called. Subsequent writes by the child process to the standard output file descriptor. Subsequent writes by the child process to the standard output file descriptor. For example, by routines such as printf, will then be routed transparently to the newly opened file instead of the screen. Okay, I don't understand this part. Okay, here. I'm just going to copy this. Close to route. FD is equal to 1. FD1 is now free. Open new file txt, OS assigns the lowest, free D, which is 1. And now FD1 points to the file. What if multiple to another FDs are per process? Each process has its own FD table? Right. Okay. Yeah, that makes sense. Yeah, why did I forget this? Okay, I'm so sorry. I'm so sorry. I'm so dumb. Okay, bro. Right. So what are the default FDs for a single executable? It's a read, yes, input, output, and error. Yeah. Cool, 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 cool. Okay, I get it. I get it. I get it. You don't know me, son. Get it. You don't know me, son. Get it. You don't know me, son. Just copy this. Yeah, we need to create a text box now. Oops, sorry. Oh my god. Okay, I hope nothing is damaged. Yeah. So we are over here. Cool. Yep, here it is. Text box. We'll drag it over here. Fill it with this. I should reduce the text size, right? Subsequent writes by the child process to the standard output file descriptor, for example, routines such as printf will be transmitted to this. Okay, cool. You will notice at least two interesting tidbits about this output. First, when P4 is run, it looks as if nothing has happened. The shell just prints the command prompt, right? Because all of the output was gone, went to P4 dot, no, what was it? All of it went to, wait, what is P4? Huh? Huh? Yeah. You notice these two interesting out tidbits about this. However, this is not the case. Wait, the shell just prints the command prompt and is immediately ready for your next command. However, this is not the case. The program P4 did indeed call fork to create a new shell and then run the WC program via call to execvp. You don't see any output printed to the screen because it has been redirected to the file P4 the output. Second, you can see that when we cat the output file, all the expected output from running WC is found. Cool, right? Unix pipes are implemented in a similar way, but with the pipe system call. In this case, but with the pipe system call. In this case, the output of one process the is connected to an in-kernel pipe that is Q, and the input for of another process is connected to that of to that same pipe. Thus, the output of one process seamlessly is used as an input for the next. Right. And long and useful chains of commands can be strung together. As a simple example, consider looking for a word in a file and then counting how many times, say, the word occurs with pipes and utilities with grep and wc. Right, you run grep and wc. It's easy, just type grep dash o output foo file output foo file wc dash l the command prompt and marvel at this. Yep, okay. Finally, while we have sketched out the process API at a high level, there is a lot more detail about this. Okay, sorry. Finally, we have just sketched out the process API at a high level. There is a lot more detail about these calls. Uh, at a high level, there is a lot more detail about these calls out there to be learned and digested. We will learn more, for example, about file descriptors when we talk about our file systems in the third part of the book. For now, suffice to say that the fork exec combination is a powerful way to create and manipulate process. Yep, cool. So this was the P4. Okay. RC, else RC, close stood out file number. So child redirects standard output to file. So we close. Uh, okay, what does close do? Stood out file number. So we close the file descriptor and then we open P4 output. So the file descriptor goes to this. So we need to manually do this. Okay, this, and then exit VP. O create, O wrongly, O trunk. SIRWXU, XWC. Right. Yep, cool. Process control and uses beyond fork, exec, and wait. There are a lot of other internet interfaces for interacting with processes in Unix system. For example, the kill system call is used to send signals to a process, including directives to pause, die, and other useful imperatives. For convenience, in most Unix shells, certain keystroke combinations are configured to deliver a specific signal to the current running process. For example, Control C sends a SIGINT interrupt to the process, normally terminating it, and Control Z sends a SIG, SIG stop signal, then pausing the process in mid execution. You can resume it later with a command. For example, the fg built-in command found in many shells. Oh, wait, you can do that. Okay, so if I were to do this, I have not tried this, so I'm just going to write into main bubble. I am going to need IO. So while just declare a variable y is equal to 0, is true not a thing. And I'm missing something. Wait, what? What? Is it like this? While true. Yeah, while true makes sense. Am I dumb? While true. Wait, what? Yup. Right. So what's the problem with this? Use of undeclared identifier true. What? Am I dumb? 22 imported? Ah, stood bolt edge. Okay. Oh, cringe. Super cringe. I mean, it's fair, you know. Wait, I messed up. Okay. So if I were to do this, so I'll do Control Z. So 4716597. And if I do FG, let's go. So now FG shouldn't work, right? Yeah, no current job. Yep, cool, 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 cool. I'm learning a lot of new things, right? Cool, crazy, crazy. Run a process. The entire signal subsystem provides a rich infrastructure to deliver external events to processes, including ways to receive and process those signals within individual processes and ways to send signals to individual processes as well as entire process groups. Okay. Aside, read the friendly manual, read the man pages, read the friendly man pages or something. RTFM. Read the friendly manual. That's what it means, right? Yep. Many times in this book, when referring to a particular system call or library call, we will tell you to read the manual pages or man pages for short. Man pages are the original form of documentation that exist on the Unix systems. Realize that they were created before the thing called the web existed. Spending some time reading man pages is a key step in the growth of a system programmer. There are tons of useful tidbits hidden in those pages. Some particularly useful pages to read are the man pages for whichever shell you're using, example TCSH, or Bash, and certainly for any system calls your program makes in order to see what return values and error conditions exist. Finally, reading the man pages can save you some embarrassment. When you ask colleagues about some intricacy of fork, they can simply reply RTFM, right? Read the friendly manual, bro. You know, it's a friendly way to say that. This is your colleagues way of gently urging you to read the man pages. The F in it just adds a little color to the phrase. Yeah, I mean it was okay. The entire signals these okay. The entire signal subsystem provides a region for us to deal with external subsystems, including the ways, space, and ways to send signals to individual processes as well as interprocess scripts. Right. To use this form of communication, a process should use a signal system call to catch various signals. Doing so ensures that when a particular signal is delivered to a process, we to use this form of communication because called a signal system call to catch various signals. Doing so ensures that when a particular signal is delivered to a process, it will suspend in normal execution and run a particular piece of code in order to in response to the original signal. Okay, read elsewhere to learn more about signals and their mean integrals. This naturally raises the question: you who can send a signal to a process and who cannot? Generally, the systems we use can have multiple people using them at the same time. If one of the people can arbitrarily send signals such as SIGINT, right, that's not fair. Like terminating it, the usability and security of the system will be compromised. Yeah. As a result, modern systems include a strong conception of the notion of a user. The user, after entering a password to establish credentials, logs in to gain access to the system resources. The user may then launch one or many processes and exercise full control over them, pause them, kill them, etc. Users generally can only control their own processes. It is the job of the operating system to parcel out resources such as CPU, memory, and disk to each user and their processes and meet overall system goals. Right? Cool. This is almost 6 months ago. Similar. Cool. Okay. Useful tools. There are many command line tools that are useful as well. For example, using the PS command allows you to see which processes are running, read the man pages for some useful flags to pass to PS. The tool top also is quite useful. Yep, top is good. I've used top as it displays the process of the system and how many CPU and other resources they are eating up. Humorously, many times when you run it, top claims it is the top resource hog. Yep. I would have shown it right now, but my other laptop isn't working. Of course, if I run this over here, it's not going to be showing top as the top one. Okay, it showed it temporarily, but OBS is the main hog. As you can see, 58% of the CPU. Yeah, cool. What if I moved a bunch? Yeah, nothing. Okay. Uh, yeah. By the way, I thought about moving a bunch because I thought like, okay, what if I move a lot of pixels continuously? Maybe they are doing some kind of like look at the camera, okay? The shades drop sometimes. See, the shades drop. Okay, the shade is gone. If I come closer, the warmer shade, colder shade, warmer shade, colder shade, warmer shade. Right. I did it like absolute cinema, you know. Oh, 60. Okay. Yeah, I should close it. Perhaps it is a bit of an egomaniac. Yeah. The command kill can be used to send arbitrary signals to kill, as can a slightly more useful friendly kill all. Be sure to use these carefully. If you accidentally kill your window manager, the computer you are sitting in front may become quite difficult to use. Finally, there are many different kinds of CPU meters you can use to get a quick glance understanding of the load on your system. For example, we always keep menu meters from Raging Menace software running on our Macintosh toolbars. We can see how much CPU is being utilized at any moment in time. In general, the more information about what is going on, the better, like millimeters. The thing is, I don't really want to know how good is the CPU utilization at a given point. You know, that's just not really an important information for me. It's just if it's just running, it's running, right? If I care about it, then sure. But right now, I'm reading a book. I don't want to see it every single time. Yep. Okay. So what I will do is I'll just ps command allows you to see which process is running. Top is quite useful as it displays the process of the system and the CPI. They already know top. Just do top is quite useful. Yep. A system generally needs a user who can administer the system and is not limited in the way most users are. Such a user would be able to kill an arbitrary process. Example, if it is abusing the system in some way. Even though that process was not started by this user, such a process should also be able to run powerful commands such as shutdown, which unsurprisingly shuts down the system. In Unix-based system, these special abilities are given to the super user, sometimes called root. While most users can't kill other users' processes, the super user can. Being root is much like being Spider-Man. With great power comes great responsibility. Thus, to increase the security and avoid costly mistakes, it's usually better to be a regular user. If you do need to be root, tread carefully, as all the destructive powers of the computing world are now at your fingertips. Right. So the thing is that power off does not work. I have tried it. Please don't work. Yep. See, it doesn't work. I did not try sudo. That wasn't the password. And I am scared. Okay, thank God. Okay. Cool. Okay. Unix system. While most users can't kill this is a yeah, for sure. Summary. We have introduced some of the APIs dealing with Unix process creation, fork, exec, and wait. However, we have just skimmed the surface. For more detail, read Stevens and Rago, of course, particularly the chapters of process control, process relationships, and signals. There is much to extract from the wisdom therein. While our passion for the Unix process API remains strong, we should also note that such positivity is not uniform. For example, a recent paper by systems researchers from Microsoft, Boston University, and Eth- Ethereum, ETH, Switzerland details some problems with fork and advocates for other simpler process creation APIs such as Spawn. Read it and related work it refers to understand this different vantage point. While it's generally good to trust this book, remember too that the authors have opinions. Those opinions may not always be widely shared as you might think. Right? Definitely, I understand your opinions. Right? You guys say like Emacs is better. Definitely. So these guys from the Church of Emacs, they do know the true power comes from them. Okay. Yeah. Church of Emacs versus the Cult of Lund. I'm from the Cult of Lund. Yeah. I would never have become a Emacs guy. Like I did not know about Emacs until I was very deep into the Vim itself. That's when I started to get memes about like what Emacs is. Right. Aside key process API terms, each process has a name in most systems. That name is known as process ID. Cool. For system call is using this to create a new process. The creator is called the parent, and the newly created process is called the child. The child process is nearly identical to a copy of the parent. Yeah. The wait system call allows a parent to wait for its child to complete execution. The exec family of system calls allows a child to break free from its similarity to its parent and execute an entirely new program. The Unix shell commonly uses fork, wait, and exec to launch user commands. The separation of fork and exec enables features like input-output redirection pipes and other cool features. Also, all without changing anything about the programs being run. Process control is available in the form of signals, which can cause jobs to stop, continue, and even terminate. Process control is available in the form of signals. Yep. I need to read about signals though. I'll just write it down because I do need to understand signals, what they are, right? Which process can be controlled by a particular person in is encap is encap is encapsulated in the notion of a user. The operating system allows multiple processes onto the system and ensures users can control their own processes. A super user can control all processes and indeed do many other things. This role should be assumed infrequently and with caution for security reasons. Cool. So we have references. Yup. Oh, okay, cool. I'm going to highlight that because that is very useful. Homework. This homework focuses on fork.py, a simple process creation simulator that shows how processes are related in a single familiar tree. Read the relevant README for details about how to run the simulator. Run fork.py-s10 and see which actions are taken. So let me just go into fork.c. So yep, I think it's in the projects. No, homework. Yep. This is yeah, process API, chapter process API video. Hmm. So let's go ahead to GitHub here. Okay, let's look at the GitHub. Ramsey Apache the saw. Well, this is CPU API. So I have fork.py. Let's look at readme. There are now two simulators related to this chapter. The first, fork.py, is a simple tool to show what a process tree looks like when processes are created and destroyed. Read more about it here. Okay. Uh, readme fork. The second program is a generator py that creates real C programs that use fork, wait, and exit to show how fork works in running programs. So don't read more about it here. Yeah, okay. So okay, I should be reading this. Fork S4 process tree. So A forks B, A forks C, B forks D, E exists, A forks E. What is happening? Okay, you know what? My mind isn't working at all at this point. I don't think I should be going ahead. Like it's 1 o'clock. I have to get up in 7 hours. I just have, yeah, okay, it's going to be 15, so I have 6 hours 49 minutes of sleep. Uh, Not bad, not bad. Okay, I think I'll just end it over here. I'll complete the homework though. Yep, I think. Okay, I cannot promise this that I will complete the homework, but I'm going. I'll try. It seems fun. TF and together, yeah, okay, a bunch of flags that I need to understand. I did this yesterday, and it's fine. It's actually even slightly easier one. Generator is fine. Generator is mostly uh, the thing that is just creating the process, so we don't really need to look into that in depth. What is important is 4.py. Yeah, it's a small code. Yeah, okay, sure. So yeah, so yep. Thanks for watching this video. This is Prashant, and I am an engineer for fun. Bye.